bienvenidos a esta nueva entrega de las entrevistas que estamos haciendo en Congreso Futuro 2025. Recordarles que estamos transmitiendo desde el Centro de Extensión del Instituto Nacional esta 14ª edición de Congreso Futuro, donde reunimos a las más grandes mentes del mundo para pensar, para construir nuestro futuro. Justamente la pregunta de este año es ¿qué humanidad queremos ser? Y para ello vamos a tener desde filósofos a físicos. Y justamente hoy me encuentro con una de las figuras más destacadas de este Congreso Futuro. Él es Serge Haroche, el Premio Nobel de Física del año 2012, quien actualmente se desempeña en la École de France y también en la Escuela Normal Superior de París. Un placer para mí presentarles, profesor Serge Haroche.
No.
A pleasure to have you
Pleasure.
here. I want to ask you so many questions, but my first one, you mentioned in your book, by the way, I have it here, La Luz Revelada, that at the beginning you wanted to become an astronomer. You were fascinated by the cosmos, but then you become a physicist and now a Nobel Prize laureate. How was that transition from your passion to the details of science?
I think it's not so much a translation because I was interested in astronomy when I was young, and it was a very interesting time because it was a time when the first rockets were launched, satellite and to the moon, and so it was a kind of adventure, physical adventure, not only science. And I was fascinated by the fact that you can compute the trajectories of rockets, the speed that a satellite should reach to be on the orbit around the Earth, or the speed you have to give to a rocket to go to the moon, just with simple calculation I could do in high school. And so I was fascinated by the connection between mathematics and the physical world. And this you find in all kinds of physical domains. And after that, when I went into what we call a Grandes Écoles in France after high school, I found that in quantum physics you have the same thing. To understand how atoms behave, you have to know a lot of mathematics, and that nature obeys to mathematical laws. So I think there is a continuity between astronomy and physics, and also to chemistry obeys to the same laws. So, but what fascinated me is the fact that you can understand the world in mathematical terms. Of course, this is not new. I think the Greeks knew that already, and Galileo already discovered that in the 17th century, that the world is mathematics. And today we are attending to lectures on quantum information. Again, it's a mathematical game.
Yeah, it was fascinating how the science evolved in these last decades. You mentioned it was not a transition from astrophysics to physics. It's incredible how it's connected through mathematics, the big galaxies, through the atoms. So I want to go like linearly a little bit in your career. You had the chance to study with great minds in the 20th century, like Koen Tanuji, for example, and other great physicists. How did you get in love, or you get your passion through the tiny atoms and try to manipulate them?
No, you are right to mention the mentors. I think it's very important in science to be lucky to have good teachers, to be trained by good people. Koen Tanuji and Kastler were really charismatic figures. They were teaching, they were giving us this enthusiasm for research, for knowledge, and they were able to present things in a new way, and this was very helpful. In fact, when I had a lot of good teachers at École Normale Supérieure, but this one was the one who related to my own way of thinking more closely than others. Another very great guy who was teaching at that time is Pierre-Gilles Degène, who was a great specialist of condensed matter physics. But I prefer to go into atomic physics because the connection with mathematics, the framework of quantum theory is a very simple mathematical framework. And I was attracted. People think that quantum physics is difficult. It's not, mathematically it's not difficult. It's difficult because it's counterintuitive, that's the point. But it's true that you have to be in the right environment to appreciate that, and I was lucky to do that. What I want to add also is that when I started, I was lucky to come into a lab which was doing experiments at the time when the laser was invented. And the laser is a fantastic tool to investigate the microscopic world. In fact, the laser has been around for 60 years. When when I started, it was in its infancy, but we imagined that it would be useful, but we could not dream about all what has been achieved during these 60 years in laser science. It's absolutely fun. The public thinks about the laser, the application of the laser, like reading the code bars or supermarkets, or reading DVDs and CDs, or the internet, the fibers in the internet. But this is applied science. But in fundamental science, the laser has played a fantastic role too. Gravitational waves have been detected because of the laser. You can manipulate single atoms because of the laser. You can cool matter to ultra low temperature and find new phases of matter because of the lasers. And I could go on. It's really something a tool which has opened many, many fields of basic science.
Yeah, definitely. You go through an elevator and the door doesn't close because of a laser, and then you also have in observatories you put a laser and mimic the atmosphere movement and all that. It's amazing how much application have. You mentioned something that I find really interesting. You can use lasers to slow down atoms, and this is part of your research during your career, studying individual atoms.
Yeah.
How is that possible? How can you manipulate through laser technology?
Yeah, that's something which developed during my career. In fact, when you excite an atom with light, the atom goes to an excited state, then it re-emits light. And this cycle repeats itself very, very fast. Atoms can reabsorb and re-emit light. It means that a single atom can emit millions of photons per second. And it's a big signal. If you look into a microscope, you see the atom as a bright star. So you can see single atoms. You can also control them with light, because light exerts forces on atoms. And you can these forces are very strong because they vary the interaction between the atom and the light varies at a very short length scale. And the force is the strongest when the distance over which it varies, the energy varies, is smallest. So you have huge forces which can keep atoms steady. You can also use laser light to decrease the velocity of atoms, and the velocity of atom is directly related to temperature. The atoms in this room, the molecules in this room, fly at something like 500 meters per second. Yeah. But you can slow them down practically. They become still. They move at millimeter per second, and then they fall. So to prevent them from falling, you have to exert forces on them and to trap them with laser light. And we learned that over the last 2 or 3 decades. Now we can use lasers to cool down atoms, to trap them, to observe them, to manipulate them. And this is something which is developing in the field of quantum information.
Yeah, that I find this fascinating, because you're talking about how the matter interacts with the light. So basically, through light and matter, like now the reflection in our face and all that, you can interact and slow down. I find fascinating. So how? I mean, you mentioned in your talk here at Congreso Futuro that sometimes you just study things like basic science, basic research. What did you want to learn about this? Because I will ask you later about the applications, but what did you want to know at the beginning? What was the questions that drives you to this research?
Okay, the laws of quantum physics have been discovered exactly 100 years ago. Mm-hmm. They are very counterintuitive. For example, you have the superposition principle, which says that a quantum system can be a different state at once. It can be suspended between different classical realities. So this is something which was theoretical at first, but now we can observe it. We can do interference experiments which reveal this feature. And so what we wanted to do is to meet a challenge, to make sure that we can do that. It's not only a kind of dream for thought experiments, but it can become real experiments. And we thought about that even before thinking about quantum computing or quantum information. In fact, we did that just because it was a challenge, a technical challenge, and whether we would be able to observe this phenomena. When I started in the 1960s, I had a cell, kind of enclosure, in which we had billions of atoms. and I shine light on these atoms, and I saw effects occurring in a big sample. But I knew that each atom in the sample was obeying to quantum rules, and since then my dream was to be able to decrease the number of atoms until we stay with only one atom and one photon to observe these fundamental effects. So it was not unexpected, because what we found, and this is what is amazing, that the founding fathers of quantum physics understood that even if they were not able to do the experiments, they imagined the experiments, and now what we are doing is to realize really in the lab what they had imagined, and the goal being to try to harness that, to use that for practical application. But our first goal was not practical application, and I still don't know really what the practical application will be.
Yeah, certainly that's something I find fascinating. I have to admit, I'm very honored to be interviewing you, because I admire this. When people think and write the theory, they say, yeah, it might never be proved by experiments. And then came the experimental physicists and designed an experiment to just try. You just mentioned, I wanted to have one atom with one photon. It's so hard for people, for me, for everyone, to think in a single ray of light, a single quantum particle. Is that possible now? Can we see one photon, or can we capture one atom?
Yeah. In fact, you see in many labs in the world, you have lattices in which you can put atoms in a lattice like you put eggs in an egg box. And so you can arrange the atoms. When you do the experiment first, you have one box is filled with an atom, the next box is empty, statistically. But if you look at it, you can pick atoms on the side and put them in the empty places, so you can rearrange these atoms one by one. And this is called quantum simulation. In this way, you simulate what would happen in a real condensed matter system, but at a quite different scale. In real matter, the atoms are 1 or 2 angstroms apart. In this artificial system, the atoms are micrometers apart. So it's much more diluted, which means that you can see much better, and you can look at the correlation between the atoms much better. So you simulate what happens in the real world with these artificial systems. The hope being that you will be able to synthesize new materials in this way.
That's great. So you mentioned this was started in the 1960s, 70s, and then you find some applications. Now, you talked about quantum computing, quantum metrology, and other stuff. How was this? I don't want to say transition, but this application. Is there an effort from your lab, or other people got interested in this and developed the ideas?
Yeah, it's a mixture of interest. First comes from the academic world, and then when there is a hope that something marketable can be produced, you have startup companies which start to be interested in that. Usually people who have been in academic research and who jump into this adventure, because it's an adventure. Most of the time it will fail, but the reward, if it works, is tremendous. So a lot of people are trying that. So it's a kind of combination, but there's aspects that I like and aspects that I don't like. And I don't like what I think overselling. The fact that, in my presentation I showed what people thought in the year 1900 about what would be the technology in the year 2000. They completely missed the point. And I am afraid that now, when we have this kind of speech, where people from IBM or from Google come and they have fantastic presentation, it's public relation. But if you look at that thing in 50 years from now, maybe you will find it very naive and completely out of. The beauty of research is that it's not predictable. And you have to be careful. And what I don't like the hype about the real quantum computer, because it's very, very far away. People don't realize that to be able to control millions of atoms without any error, without any interference with the environment, we are very, very, very far from that, and it's not sure that it will become real. But in the way to go there, or in the way, quite by chance, you can discover things which are interesting. Like when Röntgen discovered the X-rays, he was not looking for X-rays. but you develop the technology as far as you can, and something unexpected may happen.
Yeah, I want to keep that in mind because we need to do a short break and then I come back with a few more questions on that regard.
Okay.
Vamos a hacer una pausa. Estamos conversando con el Premio Nobel de Física del año 2012, Serge Haroche, aquí en Congreso Futuro 2025, donde nos preguntamos qué humanidad queremos ser y cómo podemos presenciar el futuro desde ahora. Así que los esperamos tras una breve pausa. Ya estamos de vuelta aquí en Congreso Futuro a través de las pantallas de TV Senado, donde nos encontramos aquí en el Centro de Extensión del Instituto Nacional para tener Congreso Futuro 2025, respondiendo a la pregunta de qué humanidad queremos ser. Recordarles que todas las presentaciones, incluidas la de quien me acompaña hoy, Serge Haroche, Premio Nobel de Física del año 2012, están disponibles en todas las redes de TV Senado y también a través de congresofuturo.cl y los invito de todas maneras a que las puedan buscar. Ahora volvemos con Serge Haroche para poder seguir discutiendo sobre física cuántica y un poco más de computación cuántica. Serge, we were discussing on quantum computing, one of the applications of the things you researched during several years. We know there is a lot of hype in that regard, right?
Yeah.
But the first computers are out there. What are the promises, or what do you think about that?
First of all, the first computer are just toys. To have a quantum computer working, you would need millions of bits, millions of qubits. Now the largest machine we have a few tens of bits. So this is something. First of all, these are just toys, and second, you can simulate that with classical computers. A classical computer can predict everything that will happen with up to 50 atoms. So for the time being, it's just some kind of research training. When you have a young student or young researcher working on a quantum computer, they could work as well on a classical computer emulating a quantum computer. So we're still at this stage. The problem with the real quantum computer is the same problem as the Schrödinger's cat. Schrödinger cat is a macroscopic system which is in superposition of two quite different states, and this superposition is preserved as long as you don't look at it, as long as you don't couple it to the external world. A quantum computer would be a kind of huge Schrödinger cat which would be able to calculate in a superposition of all kinds of passes in the calculation. And the slightest perturbation due to the coupling with the environment would destroy it. So the challenge is to be able to follow up all the possible perturbations and correct them as they arrive. And for that, you have to use state superposition and entanglement. You have to use all the quantum laws in order to fight against what we call decoherence. And it's very difficult, and it has not been achieved yet in a way which would allow a real quantum computer to be something useful. And there are many candidates now. You have ions in traps, you have neutral atoms in laser traps, you have superconducting qubits, which are artificial atoms, circuits at very, very low temperature. And these systems have their advantages and their problems, and which system will overcome is not yet known. And it's not even sure that the dream of a real quantum computer will come true. No.
But still, I mean, the people is doing a lot of research on these areas.
Yeah.
You don't know where they will go, right?
No,
it's hard to predict.
We don't know, but we know already now that these quantum laws, entanglement, state superposition, help to develop new probes, new measuring devices, which are much better than they were before. One domain in which you have huge progresses is the measurement of time. Clocks, which take advantage now of quantum effects to make the clock more precise. The precision of clocks now is absolutely fantastic. You know, the clock of the GPS, the clocks which we use on GPS, are precise to about 1 billionth of a second per day. It's called 10 minus 14. But the clocks the quantum clocks which are developed now are 5 orders of magnitude more precise. That is, if you use them in the GPS, you'll be able, if you have no atmospheric disturbances, to locate yourself at a precision of about 1 micrometer on the surface of the Earth. So it's unbelievable. These clocks are so precise that they can observe general relativity effect. You know that Einstein discovered that space-time is curved, which means that the time does not elapse at the same rate at different points in space. If you are close to a mass, to a big mass, the time is going slower than if you are far from this mass. It has been observed from the Earth to a satellite because it's hundreds of kilometers. But now you can see the difference on 1 millimeter with these clocks. And one of the applications that people have been thinking of is to look at the variation of the density of matter under the Earth. Mm-hmm. If you move the clock and if you have a big mass of matter, the clock will go slower. Yes. If the underground moves a little bit before an earthquake, for instance, you could have in the future observatories which will be able to get a signal, a precursor of an earthquake. And that one of the big scientists doing this kind of research is a Japanese guy, Katori. Mm-hmm. And of course, Japan, like Chile, are very sensitive to earthquakes. Yeah. So this would be an application which we did not think about 10 years ago. And it could be, and of course it's also basic science because the connection between gravitation, general relativity, cosmology is very deep and very unanswered questions that this kind of clocks can help solve. So that's one application. I talked about quantum simulation, the fact that you can simulate molecules by putting the atom at a well-defined position, and people think that it would be useful maybe to synthesize new drugs using quantum simulation. So it's still open, and I'm not sure. And I think the researcher who would do that should do it quietly and not claim that they will make a revolution or change the world. I always compare the kind of hype that we have today with what happened 100 years ago. I never heard, or I never wrote Heisenberg or Bohr or Einstein said that they were doing a revolution. They just were doing it without quietly.
Yeah, they were doing basic science on the theory side.
When I mentioned in my talk, the first two-level system was discovered by Otto Stern, who was a German who got a Nobel Prize 20 years later. He discovered the first qubit, in fact. But he did not claim in the words that he had done that. He just sent a postcard to Bohr, Niels Bohr in Copenhagen, and it was just private exchange, and nobody cared in the world. Nobody was just saying, oh, this is fantastic. Now I think we live in a time where everything has to go public, where you have to advertise everything, and we live in it's not only in science, it's everywhere, and this is a big problem.
I would like to drive you to a slightly different change. You're a person who does the right questions or have done it in the past. And one thing that fascinates me is one of the phrases you actually write it in your book. I heard it in the school or in the university. It's like when people from quantum mechanics developed the theory, you said the mathematics were not extremely hard, and people said this phrase like "shut up and calculate," because they didn't have like an interpretation. Or actually, as far as I know now, there is no one interpretation of quantum mechanics. And also, there is a problem that the quantum mechanics and general relativity don't get along very well. So I would like to, what are your thoughts on this, and what does it mean, the interpretation of the theory of quantum mechanics, and then go to this clash?
I think at the core of this problem, you had the debate between Einstein and Niels Bohr.
Yes.
Einstein was a classical physicist. Also, he helped discover quantum physics, and he had fantastic insight into relativity. He thought that the world obeyed to that was classical. He had the same as Newton or Laplace.
Yeah.
That if you could, that the world had to be deterministic. And what he did not like in quantum physics is the quantum uncertainty, the fact that a measurement changes the system in a way which cannot be predicted. And all the history, all the experiments that we are doing now say that Bohr was right, that Einstein, in fact, Einstein wanted the world to be like he liked.
Yes.
But still, as he was a very good scientist, he understood that it was not the case, and he had to do with it. So he was not happy, but he did not claim that it was wrong. He just said, I hope that one day we will go beyond that. So that was the question of, so shut up and calculate is a kind of tongue-in-cheek joke, saying that there are so many things you can do when you apply the laws of quantum physics to understand that if you lose your time into kind of philosophical question trying to answer these issues, you will be less effective than if you just use it to calculate. And that was a trend which was the general trend up to now when we are with this quantum information era. Again, the interpretation come back at the forefront. But I'm not sure it's a good thing because nobody has come with a solution which is satisfactory and which goes beyond the fact that it's still counterintuitive. In fact, the intuition is a matter of habit. When I do, when my group or my students do an experiment, they know what they expect to see, which is counterintuitive, but they are used to this counterintuitiveness, so to speak, because they have been playing with it for years. It's counterintuitive in daily life because you do not get any Darwinian advantage because you understand the quantum laws. You know, it's very important to understand the trajectory of a stone which will hit you.
Of course.
But to know whether an atom goes through two slits at the same time or not does not help you in real life. So you don't gain, the evolution has not given you this intuition. But that's what I. But it's true that at some point I find it strange. I still find it strange.
Yeah, we've 100 years and we are still don't know for sure what's the correct interpretation.
No, I know. I have the feeling that if someone tells me something which is wrong, that it will not happen. So you get a kind of mathematical intuition of what's going on.
And the other one is, well, we still, we were at a breaking point by the end of the 18th century where people discovered quantum mechanics, right?
Yeah.
And then relativity. And now we know there are experiments in observatories and in particle accelerators.
Yeah.
They are looking for dark matter, dark
Yeah.
energy, and these particles that the graviton, for example.
Yeah.
But when we try to combine this quantum physics and relativity, they don't work together.
Yeah.
Do you think we are in this verge of an abyss?
We need someone like Einstein. But not only that. In fact, Einstein based his intuition on experiments. So we need a combination of a very bright mind and also experimental data. A lot of very bright people are working on string theory.
Yes.
The problem is that there is no experimental verification. Dark matter is up to now, it's an hypothesis. Nobody has seen dark matter. Mm-hmm. You have an example of that. 100 years ago, everyone was talking about the ether. It was a medium in which light was propagating. And Einstein just said there is no ether. We don't need that. Light is propagating in vacuum. And then quantum mechanics came, and the vacuum became also again something interesting because there is a lot of virtual particles in the vacuum. And energy in the vacuum, and unknown particles which appear and disappear fleetingly. And we have to find some material evidence of that, which is not the case yet. So I don't know, but it's at the border of quantum physics, cosmology, because it's a history of the universe which is at stake to understand how it came into to happen. And this is a very, very interesting question for the future.
And you're experimental theoretical and experimental physicist in particular. What are the questions that struck you the most now? What are the things that you see you still I would like to see this solved, or I would like to solve this?
I think, of course, the issues that we mentioned, the combination, the unification between quantum physics and general relativity is a very big issue, but it's completely beyond my knowledge, but I'm sure that it will be a big question. Another thing which I think fascinating, which is pure basic science, is the search for life in exoplanets. To look, first of all, to all this physics of exoplanets and trying to find an exoplanet in which the conditions for life are realized, and maybe for intelligent life. It's also fascinating, and it's not useful because we know that we will never go there, and I think we know that we will never communicate with these people. But to know that this exists, I think, is a question that we need to solve because we are curious.
Yes, I totally agree with you. I wasn't expecting that. I was expecting something more maybe detailed on the quantum.
No, but of course, I could tell you a quantum computer,
No, but
but it's not so exciting.
yeah. Well, I mean, sometimes we have personal preferences. I would like to, well, since you're an authority in the fields of physics and you're visiting us, I would like to, what would you like to say to the students now from Chile that are looking this interview or that are here at Congreso Futuro about like your career or like follow this dream? You mentioned during the interview, like, I had these questions, I really wanted to answer it, I think an experiment. What would you say to these people?
You mean going beyond science in general about the future of mankind and society?
Yeah.
I think we live at a very difficult time. I think all what we are discussing, the science, the progress of science, the need for basic science, come from the time of Enlightenment. It happened in Europe in the 17th and 18th century. And all the society in which we live come from there. The science come from there. The idea of democracy, the idea of freedom, the idea of peace has been discussed by the philosophers, the French and the German and the British and the Spanish philosophers at this time. And we have been living through a period where we thought that these ideals would be fulfilled and it would become universal. And now we see that it's not the case, that there are a lot of people who claim that the European civilization was a colonialist and that we should go beyond that, and that there are other truths beyond that. And my feeling, because I am old, my feeling is that there is an advent that what happened in Europe is not below or at the same level as what happened in other parts of the world. The fact that we can have a society which goes beyond religion, which is not based on dogmas and religion, is an idea which came from Europe and which is very important. I was surprised when I walked near the presidential palace here in Santiago. There is a statue of a president in the 1930s, 40s, and they have a quotation by him which says that the state has to be laical and that the religion has to be separated from the state. It's exactly what kind of ideas that we have in France. And I think these ideas are very important to avoid fanaticism, to avoid obscurantism and barbarism. And we live at a time where all these ideals are in danger. And I think that if this happens, then science, the value of science and research and civilization will be also in big danger. And I am very much worried by what's going on, for example, in the United States now. They put at the head of the health ministry a guy who is against vaccination, and you can take many examples of that. I think this is, I would not have believed that I would live at a time like that. And I think this is very important. And in South America, you might think that you are removed from this problem because you are far from Europe. In Europe, we feel that very badly. We feel that there is a big danger coming from Russia now. And I think there is a huge danger of a nuclear war one day or the other. You cannot have accumulation of thousands of nuclear weapons everywhere in the world, the cancellation of all the treaties controlling the dissemination of nuclear weapons, which happen now, and seeing that this would have no consequences. We met the Nobel laureates met in Lindau last June, and we issued a statement saying that the big danger now is the danger of a nuclear war. And apparently, young people, when you talk about the danger of nuclear power to young people, they think about the civil nuclear. They say that the power plant is dangerous.
Yeah.
And the nuclear weapons, they think it's just a fantasy. But I don't think so. And I think we need to have leaders in the world who address these issues, who understand this is a big problem, and who understand that we have to try to save the values of a civilized world.
Yeah, that was a very nice closing remark. Save the values of the civilized world. Thank you very much, Serge. It's been an honor, a pleasure. Thank you very much for your time, and we'll continue here at Congreso Futuro.
It's my pleasure. Thank you.
Muchas gracias a Serge Haroch por acompañarnos hoy. También muchas gracias a ustedes por seguir esta transmisión. También el Congreso Futuro, dejarlos invitados a que vayan a las redes de TV Senado, donde podrán seguir tanto las charlas como las otras entrevistas que hemos hecho aquí en el Centro de Extensión del Instituto Nacional, en este Congreso Futuro 2025, donde nos preguntamos qué humanidad queremos ser y cómo la construimos desde los actores que están desde todas las áreas de las ciencias. Nos encontramos en otra oportunidad aquí en otra entrega de TV Senado para Congreso Futuro.